What happens if a critical system fails while the vehicle is operating? In many cases, failure is not an option. The system must continue to function, even if something goes wrong. So how is this achieved? How can a system remain safe despite failures? This is where redundancy comes into play. In this video, we explain how redundancy works in automotive systems and why it is essential for functional safety. In complex systems, failures are unavoidable. Components can fail, signals can be incorrect, or systems can behave unexpectedly. If a system relies on a single element, this creates a single point of failure, and this can lead directly to system failure. Redundancy solves this problem. By introducing additional elements, the system can continue to operate even if one part fails, and this is essential for safety-critical systems. So what is redundancy? Redundancy means using multiple elements to perform the same function. Instead of relying on a single component, the system includes additional elements that can take over if needed. This reduces the dependency on any single component, and it ensures that the system can continue to operate, even if one element fails. Redundancy is a fundamental principle in safety-critical systems. Redundancy can be implemented in different ways. One common type is hardware redundancy. This means using multiple physical components to perform the same function. Another type is software redundancy. Here, the same function is implemented using independent software solutions. And finally, information redundancy. This involves using multiple data sources or signals. In practice, these types are often combined, depending on the system requirements. Another important distinction is how redundancy is used. There are two main approaches: active redundancy and passive redundancy. In active redundancy, multiple elements operate at the same time. They all contribute to the system output. In passive redundancy, only one element is active. The backup is only used when the primary element fails. So here is a key question. Should both channels run continuously, or should the system switch only when needed? The answer depends on the system requirements and safety goals. Let's look at a practical example. Consider a system that uses two sensors to measure the same parameter. Both sensors operate independently. Their signals are continuously compared. If the values match, the system continues normal operation. But if there is a deviation, this indicates a potential fault. The system can then react, for example, by switching to a safe state or using fallback logic. This is a simple but very effective example of redundancy in practice. Redundancy and safety mechanisms are closely connected. Redundancy provides multiple sources of information. This enables safety mechanisms to detect faults more reliably, for example, by comparing signals from independent channels. Once a fault is detected, safety mechanisms define how the system reacts. So redundancy supports detection, and safety mechanisms define the response. And in safety-critical systems, both are typically used together. Redundancy is closely related to ASIL levels. As the required ASIL increases, the acceptable failure rates become lower. This is where redundancy becomes essential. For lower ASIL levels, a single system path may be sufficient. But for higher levels, redundant architectures are required. And for ASIL D, multiple layers of redundancy and monitoring are often necessary. There are several common mistakes when using redundancy. One of the biggest misconceptions is assuming that redundancy automatically ensures safety. Simply having two elements is not enough. If both channels rely on the same components or share dependencies, they can fail at the same time. This is known as a common cause failure. Another mistake is missing proper monitoring or comparison. Redundant elements must be evaluated. Otherwise, faults may go undetected. And finally, overcomplicating the system. Redundancy should improve safety, not introduce unnecessary complexity. Let's summarize the key points. Redundancy ensures that a system can continue to operate even if a failure occurs. Different types of redundancy can be applied depending on the system design. Active and passive redundancy represent different approaches. A key requirement is independence between elements, and redundancy is a fundamental concept in functional safety. If you want to deepen your understanding of redundancy and system design in ISO 26262, we offer comprehensive online training programs on our website. These self-paced courses cover topics such as ASIL, safety mechanisms, redundancy, and system architecture in a structured and practical way. The focus is not only on understanding the concepts, but on applying them in real engineering projects. You can find the link in the video description and also in the pinned comment below. If you found this video helpful, feel free to give it a like and subscribe to the channel. We regularly publish content on functional safety, ISO 26262, ASIL, ASPICE, and other engineering standards. Thank you for watching, and we look forward to seeing you in the next video.